Hi there, and thank you so much for joining me today. So this is going to be the last video in Module 8, which provides an introduction to statistics. And in this video, I'm going to talk about z-scores. Okay, so I want to return to a concept that I discussed in my last lecture on measures of variability, and that's something called the empirical rule. So anytime you have a data set or a variable that you're measuring that follows what's called a normal distribution, that distribution is going to follow something called the empirical rule, right? So essentially what that means is that most of the scores in your distribution are going to fall somewhere in the middle, kind of meaty part of the curve. So for example, 68% of your scores are going to fall within one standard deviation of the mean, right? And the standard deviation is just the average deviation or the average distance from the mean of all of the scores in your distribution. So 68% of the scores are going to fall within one standard deviation. 95% of the scores are going to fall within two standard deviations. And 99.7% of the scores are going to fall within three standard deviations of the mean. Right? So why does this matter, or why is this important? Well, normally distributed data, or data that approximates a normal curve, when we create a frequency graph like a histogram and trace a line over the frequency bars, right? If what we get is a normal curve, that means it's going to be perfectly symmetrical. The mean, median, and mode are all going to be equal to each other, right? And because we have the empirical rule, we can start to estimate certain probabilities, right? So like I said, in the dark orange there, that accounts for 68% of the scores that fall within one standard deviation. The sort of tan color there is going to account for the 95% of scores that fall within two standard deviations. And the yellow part there is going to account for scores that fall within three standard deviations. And if you add all of those up, you will get 99.7, right? Or if you add all the orange ones up, you'll get 68. If you add the tan colors, so that's 68, you'll get 95. And if you add the yellow, then you'll get to 99.7, right? So once we graph our normal distribution in this way, okay, it allows us to start estimating the probability of getting any particular score by chance, right? So for example, let's say you meet a random person on the street, right? So using the above graph, what is the probability that that person has an IQ above 115, right? Well, let's locate 115 on our graph here, right? So anyone who has a IQ above 115, right, is going to have the associated probabilities of a score above 115 are going to be included in the shaded area under the curve, okay, right where that line that 115 sits on, right? So that would mean 13.59, okay, in that tan colored shaded area, plus 2.14% plus 0.13, okay? So all of the area under the curve to the right of 115 would show us the probability that we're looking for, right? So 13.59, okay? If we add 13.59 and 2.14 and 0.13, we get a probability of 15.86. Okay, so there is a 15.86% chance that a random person in our distribution is going to have an IQ score above 115, right? And said differently, okay, 84.14% of people are going to have a score at or below 115, okay? So the area to the left of the curve is going to account for those individuals who have a score at or below 115, okay? And if you added up all of the associated probabilities, okay, 34.13 plus 34.13 plus 13.59 plus 2.14 plus 0.13, you would get a probability of 84.14. Okay, so provided our data is normally distributed and approximates a normal curve, we can actually estimate the probability that a person has an IQ score either above or below whatever our metric is. Okay, so we can actually glean a lot of information simply by graphing our distribution, provided it's normally distributed. So you might be wondering, what if our distribution or our data set isn't normal? Well, in statistics, we assume that if our sample size is large enough, and typically that means that our sample has at least 30 observations, right? So if n is equal to or greater than 30, then we can assume that our distribution will be normal enough to approximate the normal curve, okay? And in addition to that, we also have the software program that you guys downloaded for free this week, SPSS, which can run a variety of tests for us to see if our data approximates the normal curve or if it's normally distributed. Okay, so that's the normal distribution and all of the things we can do if we know that our data follows a normal curve. Okay, so now that we understand a little bit more about the normal curve, let's go ahead and talk about our topic for today, which is Z-scores. So again, we know about the normal curve. So if I were to take any one value in this distribution, right? So any one of the scores at random, right? So remember, any single observation is denoted by an X. So if I were to take any random score from this distribution or any value of X, that value is going to provide very little information about how that particular score compares with other values in the distribution, right? So for example, a score of 115 might be a relatively low score or an average score or an extremely high score, depending on the mean and standard deviation for the distribution that the score was obtained from, right? So we see here that the mean of the distribution, the sample mean, is 100. It's right in the center there. And that the standard deviation is 115, right? So we know that a score of 115 is one standard deviation above the mean, okay? But that information can be used to calculate a z-score, okay? And the z-score tells us exactly where the score is located relative to all of the other scores in the distribution, okay? So what exactly is a z-score? Z-scores are standardized scores, meaning they allow us to compare scores from many different distributions, okay? So we can actually look at the relative position of scores from across a variety of different samples or different distributions, even when those distributions have different means and standard deviations, right? So a person's z-score is the number of standard deviations that lie between their score and the sample mean. Okay. So again, it tells us the number of standard deviations that lie between their score, or our value of x, and the sample mean. Okay, so the formula that we're going to use to calculate z-scores is simply the x, which is the individual score that we've obtained from the sample, minus the sample mean divided by the standard deviation. Okay? So sticking with the IQ distribution from the previous slides, where the sample mean is 100 and the sample standard deviation is 15, we could calculate the z-score for a person with an IQ of 120. Okay. By inputting those values into the formula, right? So we have 120 is our score, our individual score. 100 is the sample mean, and we divide that by 15, which is the standard deviation. Okay, so we end up with 20 divided by 15, which is 1.33. Okay, so what does this value mean? Well, we can look at the sign of the number, and we can look at the number itself, the value, okay? So this is a positive 1.33. So we know that this person's score, the person who scored 120, their score is above the mean because the value of the z-score is positive, okay? And the number itself, the 1.33, tells us how many standard deviations above the mean that score is. Okay, so that score of 120 is above the mean because the z-score is positive, and it's 1.33 standard deviations above the mean. Okay, so just to recap, when we change a given value of x into a z-score, essentially what we're creating is a number, okay, where the sign of the z-score, whether it's positive or negative, tells us whether that individual score or value of x is located above the mean or below the mean. Okay, so when we see a z-score, it's telling us that that given value of x is either above the mean or below the mean. If it's positive, it's above. If it's negative, it's below. And the numerical value of the z-score is telling us how many standard deviations that given value of x is, or it's telling us by its numerical value the number of standard deviations between that given value of x and the mean of the distribution, right? So if we know that a given value of x is 2 standard deviations above the mean, then its z-score is going to be positive 2, or simply 2. So one of the really neat things we can do with z-scores is we can convert them to percentages, very similar to what we did in the beginning of the lecture. Okay, so they can be transformed into probabilities using a distribution table. Okay, so in the module for this week, I have included a handout of this table. So I'm going to show you guys how to use this table to calculate probabilities or percentages. All right, so returning to our current example, our person has an IQ score of 120, which the associated z-score of 1.33 tells us that a score of 120 is 1.33 standard deviations above the mean, right? But how does this score compare to the rest of the scores in the distribution, or how does it compare to the population? Well, to figure this out, we can use our table, okay? So first what you're going to do is you're going to go to the Z column and you're going to find the first decimal place, right? So we're going to look for 1.3 in the column, and then we're going to look for 0.03, okay? And you're sort of going to match up both of them. Okay, so if we first find 1.3 and then we find 0.03 and our fingers kind of meet in the middle, we see that a z-score of 1.33 is associated with a probability of 0.9082. Right? Or if we multiply this probability by 100, we see that it's associated with a percentile or a percentage of 90.82%. Right? So what does that mean exactly? Okay, this person's IQ score of 120 is higher than approximately 90.82% of other people's. Okay, so a person who scores an IQ score of 120 has a higher IQ score than approximately 90.82% of people. Okay, and another way to think about it is that 90.82% of people have a score below 120. Okay? So similarly, if we wanted to find the probability of a person having an IQ score that is higher than 120, all we would have to do to calculate that percentage is subtract 90.82 from 100, okay? And we would see that the probability of a person having an IQ score that's higher than 120 would be 9.18, Okay, so just like we did at the beginning of the lecture when we looked at the distribution of the normal curve to see the percentage of people who had an IQ score higher than 115, and then we looked at the percent of the distribution who had a score below 115, right? That's exactly what we're doing with Z-scores. We're just using the table instead. Okay? Okay? So again, the associated probability here is 0.9082. We convert that to a percentage, and essentially what it means is that 90.82% of people have a score lower than 120, and only 9.18% have a score that's higher than 120. Okay? Okay? And if we return to our first example, right? Our Z-score, if we're looking at an IQ score of 115, right? We would take our score, our value of x, which is 115, subtract 100, divide it by the standard deviation, and that would give us a z-score of 1.00, right? Just like when we looked at the graph, right? And I told you that given that the mean is 100 and the standard deviation is 15, right? And I told you that a score of 115 was one standard deviation above the mean, right? That's exactly what our z-score is telling us, right? And similarly, if we were to find a 1.00 in our table, we would see that the associated probability is 84.14%, right? And that means that 84.14% of the population has a score at or below 115, right? And just like we saw in the graph, when we added all of the probabilities to the left of 115, right? 34.13 plus 34.13 plus 13.59 plus 2.14 plus 0.13, right? That gives us a probability of 84.14, and that's exactly what we find in the table. Okay, so we're doing the exact same thing. Okay, so let's work through one more example that's going to be kind of fun. Okay, so there is a very well-known, very well-established psychological test that measures the 5 most critical personality traits. Okay, so the big 5 measures openness, or consists of openness, conscientiousness, extroversion, agreeableness, and neuroticism. Okay? And there are a total of 240 items that are rated on a Likert scale, ranging from strongly disagree all the way to strongly agree. Okay? So what I would like you guys to do is look at the following scale for adventurousness. Okay? So what you're going to do is you're going to indicate using the scale below your agreement with each of these 8 questions. Okay? So for example, for number 1, I'm pretty set in my ways. Do you strongly disagree? Disagree? Are you neutral? Do you agree or strongly agree? Okay, so do that for each of these 8 items. Okay, and once you've completed that, now you're ready to calculate your score. Okay, so if you said strongly disagree, that would merit a 4. If you said disagree, that would merit a 3. Neutral, that would merit a 2. Agree, a 1. And strongly agree, 0. Okay, but once you have done that for all 8 questions, then you need to reverse score number 2, number 4, and number 6. So remember, we have some items that are reverse scored so that we can avoid response set, right? So once you've scored all of your answers using the yellow table, then you're going to go back to number 2, number 4, and number 6 and change your numbers as we see in the green table there. Okay, so if you initially wrote a 4 for number 2, number 4, or number 6, you need to change it to a 0, and so on. Okay, so once you've done your scoring and your reverse scoring, then you are going to add up your total score. So your score should be somewhere between 0 and 32. Okay, so what I would like you to do is I would like you to compare your own score to the scores typically found in the population. So we have 4 different categories depending on your age. So if you are between the ages of 17 and 20, then you're going to want to choose college age women or college age men. If you are older than 20, you're going to want to choose adult men or women. Okay? So essentially this mean and standard deviation, okay, you're going to input those directly into your formula. Okay? So your mean is going to be your mu value, and your standard deviation is going to be your sigma value. Okay, so go ahead and input your score for X, and then whichever mean and standard deviation is appropriate for your demographic. Okay, so now based on your Z-score, I want you to find out how you compare to others in the population who have your same age and gender norms. Okay, so based on the sign of your Z-score, are you above the mean? Okay, so if your Z-score is greater than 0, you're above the mean, or are you below the mean if your Z-score is negative? Okay, and by the way, if your Z-score is negative or above 2.9, you're going to have to look at the table handout. So the Z-table handout I referenced earlier, which can be found on Canvas. Okay, so go to that table once you find your Z-score and look at the percentage of people who have lower scores than you. So for example, my score on the adventurous measure was a 5, okay, and I am older than 20 by a considerable margin. I'm not going to tell you by how much. So my mean and standard deviation was 16.8 and 3.6. So when I inputted those values, I got a z-score of negative 3.28. So when I found negative 3.28 in my z-table, the associated probability was 0.005. Okay? So once I multiplied that by 100, I got a percentage of 0.05. Okay? So essentially what this means is only 0.05% of the population got a score lower than my score, right? Or another way of thinking about it, right, is that 95% of the population ended up with a higher score than I got, right? So essentially what that means is that I am not a very adventurous person, right? I'm sure if I thought about it hard, I would come up with other positive qualities about myself, but adventurousness is not one of them, apparently. Okay? Okay. So one more thing that we can do with z-scores is we can use them to compare scores from different distributions. So what do I mean by that? Well, let's look at this example. So the example says, Mike got an 88 on his math test and Joy got an 86 on her math test. Okay? Who did better? Okay. In Mike's class, the mean was 87 and the standard deviation was 4. In Joy's class, the mean was 83 and the standard deviation was 3. Okay? So we can compare across those completely different distributions to see the relative position of each of their scores compared to the rest of the scores in the distribution. Okay, so Mike's z-score, we would take his value of x, which is 88, and we would subtract it from the sample mean, which is 87. So that gives us a 1 divided by the standard deviation in Mike's distribution, which is 4. And that gives us a z-score, a positive z-score of 0.25. So that essentially means that Mike's exam score is 0.25 standard deviations above the mean. Okay? In contrast with Joy, okay, her score was an 86. So we would subtract that from the sample mean, which is 83, and divide it by her sample standard deviation, which was 3, and we get a value of 1.00. Okay, so Joy's score is 1 standard deviation above the mean. Okay, so Joy actually did much better than Mike relative to the other people in their classes. Okay, and lastly, one thing you can do is you can convert z-scores to determine a raw score, right? So when might you want to do that? Okay, well, in this example, if the mean SAT score is 1,000 with a standard deviation of 200, you might wonder, what score do I have to get in order to be in the top 10% of people who took the test, right? And you might wonder similar things when you're applying for graduate school and taking the MCAT or taking the GRE, if you know what the threshold is for the school that you're interested in, right? It would be important to calculate that. So first, what we're going to do is we're going to look at our Z distribution table and find the value corresponding to 90% and plug it into the equation. Okay. Okay, so we're going to use our standard equation for z-scores, and we're going to plug in what we have and solve for x. So the z-score corresponding to 90% is 1.29. Okay, so we're going to input 1.29 for z, and then we're going to solve for x. Okay, so once we solve for x, we get a score of 1,258.